So I welcome you to today's ECT Star introductory colloquium on pertinent science topics of the workshop entitled Neutron Stars as Multi-Messenger Laboratories for Dense Matter, which was planned for 2020 but has been deferred to 2021 because of the COVID-19 pandemic. As you know, the intention of this colloquium series is to introduce and publicize the science case for the workshop to a wider audience. Today's presentations will be shared between Anna Watts from the University of Amsterdam and Sanjay Reddy from the University of Washington and the INT in Seattle. Anna's title of the presentation will be The Neutron Star Interior Composition Explorer, or NICER in short, and Beyond, while Sanjay's presentation is entitled Dense Matter in Neutron Stars and its Applications to Multi-Messenger Astronomy. Let me briefly introduce the two speakers. Anna Watts is a professor of astrophysics at the University of Amsterdam. Her research group studies neutron stars, in particular the dense matter in their inner cores and violent dynamical events such as starquakes and magnetic or thermonuclear explosions that undergo on a regular basis in binaries. Space telescopes are a vital part of her research. Anna co-chairs the Dense Matter Science Working Group of the proposed Chinese-European Enhanced X-ray Timing and Polarimetry mission, in short EXTP. She's also part of a team working on NASA's NICER project, as will also be discussed in her presentation. And she's also a member of the steering committee for the NASA probe mission concept throwbacks in the future. Sanjay Reddy is a professor of physics at the University of Washington and a senior fellow at the INT in Seattle. For many years, he has been interested in nuclear and neutrino processes that underlie extreme astrophysical phenomena, such as neutron star structure and evolution, core collapse supernovae, X-ray bursts, magnetar flares, and gamma ray bursts. His other research interests include the application of quantum many-body theory to nuclei, cold atom gases, nuclear matter, dense quark matter, and related phases in neutron stars. I thank you both for agreeing to give these talks.
My name is Sanjay Reddy, and I'm delighted to present or share with you some of the excitement in nuclear astrophysics. A lot of different advances in multi-messenger astronomy, nuclear and particle astrophysics, and computational astrophysics are all coming together to help us observe and interpret interesting phenomena that we are observing for the first time in many cases from the universe. And in this talk, I will briefly discuss the central role neutron stars, and in particular dense matter inside neutron stars, plays and what it means for multi-messenger astrophysics. So these observations and the theory that helps interpret these observations are poised to address some big questions that have been around in the field in the coming decade. And some of these questions include what are the mechanisms that power the most extreme phenomena in the universe, such as gamma ray bursts, supernovae, etc. We've also been wondering what sorts of quantum matter may exist inside neutron stars, and theoretical speculations abound. And this might be the decade in which we actually figure out, using observations and theory, what states of matter might exist at the highest densities encountered inside neutron stars. There are also issues about understanding how the universe produces heavy elements, and recent observations are providing useful hints that neutron stars may play a central role in making heavy elements such as gold, platinum, uranium, etc. And if time permits, I will also discuss briefly how neutron stars may be excellent laboratories to study dark matter. As I mentioned, these are interesting times because multi-messenger astronomy has become a reality. For decades, we've studied astrophysics using photons across the spectrum, from radio waves all the way up to gamma rays. And neutron star science has benefited greatly from X-ray astronomy and radio astronomy. But we know that neutron stars are special in that they are probably the only source that can simultaneously produce both photons, neutrinos, gravitational waves, and also a new probe of extreme phenomena in the universe happens to be nuclei that are produced in these events. And we now have the ability to find these very rare nuclei on surfaces of stars and meteorites, etc. So putting all of this together will help us interrogate what happens when matter is at extreme densities and temperatures in the universe, and what happens in extreme phenomena such as neutron star mergers and core collapse supernovae. So this field has been driven by some recent observations, and most important of these observations have been our ability to measure neutron star masses and radii. The discovery of a 2 solar mass neutron star had a huge impact on the field, and I will briefly discuss what that is. We've been able to use radio astronomy and pulsar timing to study binary systems and extract masses of individual stars in the binary very accurately. And these 3 examples here shown in the figure indicate that we now know conclusively that very massive neutron stars with masses in excess of 2 solar masses exist. Measuring radii, which will be a topic that will be discussed in detail by Anna Watts in the next talk, has been difficult because there are poorly understood systematics that preclude using X-ray emission from the thermal spectrum of a neutron star to measure radii. However, observations that Anna will discuss from a new instrument called NICER, and most excitingly, gravitational waves from binary neutron stars provide powerful new methods to measure neutron star radii. So about a few years ago, X-ray measurements were indicating that the neutron star radii probably are between 10 and 15 kilometers. But as I mentioned, the errors associated with those inferences were large. Now, gravitational waves provide a new method to measure the sizes of neutron stars, and I'll briefly discuss that now. We've known for some time, in fact, the motivation to build instruments like LIGO was because neutron star binaries existed, and we knew that with time, these binaries would coalesce and merge. And during the final seconds of their merger, they would emit intense gravitational radiation that would be discoverable or detectable out to large distances of the order of a few hundred megaparsecs. And what this slide basically shows is what we know as the mechanism for radiation. It's just the fluctuation of quadrupoles created by 2 neutron stars that emits this radiation. And we can measure strains in detectors to the order of 10 to the minus 23, which is pretty remarkable. And this allows us to detect neutron star mergers out to very large distances in the universe. And all of this came together a few years ago in August of 2017, when we first detected gravitational waves from a binary neutron star merger. And I'm sure you've heard a great deal about it from many talks in the past few years. What is remarkable is that this measurement allows us to precisely extract many parameters of the source. For example, what's plotted here, what's shown in this slide are the masses of the individual stars, known to about 10% accuracy, and other combinations of the neutron star masses in this binary that are known to incredible accuracy, such as, for example, the chirp mass. And on the plot on the right-hand side, you see this characteristic increase in frequency of gravitational waves that arises from mergers of binaries. And from these observations, we can extract very detailed information about not only the source masses, but also about the size of these sources. And now I'll briefly discuss how one extracts the size from these observations. So when neutron stars merge, when the distance between the neutron stars becomes comparable to the radius of the neutron stars, the forces, the tidal forces of the neutron stars on each other begin to deform these neutron stars. And this produces a quadrupole moment on the neutron star. And this relationship here between the quadrupole moment and the external field is related by a constant of proportionality called the tidal deformability. It's just a measure, an intrinsic property of the neutron star that tells you, given a tidal field, how much quadrupole deformation can you produce on the neutron star. So this is a fundamental property of the neutron star, and by measuring the tidal deformability, we will be able to constrain the size of these neutron stars. So the effect of the tidal deformation is to enhance the speed of the inspiral. So tidal interactions change the rotational phase. They, in fact, accelerate in spiral, and one can measure this accelerated in spiral due to tidal interactions, and in particular due to the quadrupole deformation of these neutron stars. So the change in phase can be measured, and it is related to a combination of tidal deformabilities of the individual neutron stars, which is here, which is given in this formula by the symbol lambda tilde. So lambda tilde is the dimensionless binary tidal deformability. It is a combination of the properties of both neutron stars, and there's a very specific combination in which it appears, and that's shown in this equation here. What is interesting is that the tidal deformation of the individual stars is a very, very sensitive function of the radius. In fact, the tidal deformation of the individual stars scales as the 5th power of the radius. So a large neutron star has a very large tidal deformation. And what we were able to do, several groups around the world were able to do, was analyze the tidal deformation, the signatures of tidal deformation that might have been present in the gravitational wave emission from GW170817, the first neutron star merger that was observed. And by not finding tidal deformations in the signal, we were able to deduce a very firm upper limit on the radius of the neutron star, which is about 13 kilometers. So what this analysis led to was that an understanding that neutron stars had to be less than 13 kilometers, and concomitantly with the discovery of 2 solar masses, one can also find that the radius of all neutron stars will have to be greater than about 9 kilometers for one to be able to also accommodate a 2 solar mass neutron star. So in just the last few years, we've been able to bracket the maximum radius possible for neutron stars and the smallest radius possible for neutron stars. And this is very interesting because it implies that neutron stars are small. And this has important implications for our understanding of matter inside neutron stars. So this relationship between the mass radius of a neutron star and its internal properties is through the equation of state of dense matter. So the equation of state of dense matter is the relationship between pressure and energy density of matter encountered inside a neutron star. And there is a one-to-one correspondence between the pressure energy density curve and the mass radius curve of neutron stars. So all that one requires to see this one-to-one relation is general relativity, which has passed every test we can throw at it. So this is a very robust correlation between microscopic physics in the dense interior and macroscopic physics that one can observe through X-rays and gravitational waves, which is the neutron star structure. So different equations of state will correspond to different mass radius curves, as shown by these 2 examples here. And you can say, for example, if you have an equation of state that is soft, which means the pressure is small at a given energy density, at low density, and it's large at high density, then it would imply that the neutron stars are small, but they can also support very large maximum masses. So if you discover a small neutron star radius and a large maximum mass, it implies that somewhere inside the neutron star, there must be a rapid transition from low pressure, which allows you to produce a small neutron star, to very high pressures, which will allow you to support a maximum mass in excess of 2 solar masses. However, neutron stars are not simple objects. They're pretty complex objects. One needs to know the equation of state across several decades in density. And this figure here shows the complexity that we are currently aware of that exists inside the neutron star. So the outer 2 kilometers or so of the neutron star is called the crust. It's mostly composed of nuclei, very relativistic electrons, and a superfluid state of neutrons. The outer core is a liquid form of very dense matter containing neutrons, protons, electrons, and even muons. And at higher densities, densities that are in excess of about 2 to 3 times the density found inside a nucleus, we think that new forms of matter are likely, and there is these sub-nucleonic degrees of freedom, which we know to be quarks, will begin to emerge in some way. However, we don't quite understand, or we don't have the theoretical methodology at hand to describe where and how this transition occurs. And at the very highest densities encountered in the cores, perhaps some form of quark matter is encountered. Now, as I mentioned, pressure versus energy density, called the equation of state, is fundamental to our understanding of neutron star structure. And what this graph here shows is an illustration of what we expect this curve to look like for dense matter encountered inside the neutron star. So there are various important epochs. The crust is composed of relativistic electrons, and there's a region where even neutrons exist alongside nuclei, and that's called neutron drip. And then there is a transition from the crust to core where one encounters neutron-rich matter. So properties of neutron stars, to be able to calculate them, we need a description in terms of quantum many-body physics that allows us to calculate this relationship between pressure and energy density. So our current tools that we have, we are able to calculate reliably the equation of state up to a density which we currently think is about twice nuclear density. And there are at higher densities, there are many models, but we don't have reliable tools to calculate what the equation of state is. So for the rest of the talk, I will try to see what progress we can make by using calculations of the equation of state up to a certain density, and then some very general considerations to extrapolate to higher densities. Now, it is fortunate that calculations show that the radius of a neutron star, especially a radius of a typical neutron star that has a mass of about 1.4 solar masses, is very sensitive to the equation of state in the region where we can calculate it. So there is a good correlation between calculations that can be performed today and measurements of neutron star radii. On the other hand, if you'd like to understand how massive can a neutron star be before it collapses to become a black hole, that is very sensitive to information at higher densities, densities beyond which we can currently calculate. So let me describe the calculations very briefly that allow us to provide a description of matter up to about twice nuclear density. At these densities, it is reasonable to treat nucleons, which are the relevant degrees of freedom here, as non-relativistic particles. And one can use the methodology developed to study non-relativistic many particle systems like nuclei in the laboratory and other systems realized in condensed matter physics to study dense matter that's encountered inside a neutron star. So the starting point for such a study is a Hamiltonian that describes the interactions between neutrons that exist in the cores of neutron stars. And there are many aspects to this interaction. The most important ones are the two-body interactions between nucleons. And these have been constrained very well over decades because we have studied nucleon-nucleon scattering, and we've measured the cross-sections and phase shifts. And these provide very good constraints on the types of potentials one can use to write down this Hamiltonian. But at higher densities, interactions between 3 neutrons and even perhaps 4 neutrons become important. And these 3 nucleon potentials have also been studied in the laboratory, but not as well as the 2-body potential. And so they are not as well constrained. But developments in the last 10 years or so, based on effective field theories, have provided much guidance, much needed guidance to organize this Hamiltonian. And once you have a Hamiltonian, you still need a method to solve this Hamiltonian and get the equation of state. And those are called quantum many-body methods. There are many methods on the market today. There are methods such as quantum Monte Carlo that are non-perturbative methods. There's many-body perturbation theory, which is intrinsically perturbation theory that can be applied to even strongly interacting systems under special circumstances, and so on. So the developments that I mentioned that helped organize the nuclear forces have really revolutionized our understanding of dense matter, because by organizing the Hamiltonian in the most general momentum expansion, we are now able to calculate errors associated with aspects of the force that we don't currently know very well. So the way the effective field theory organizes the Hamiltonian is it writes down all possible operators that can up to a certain power in the momentum. And the leading order has the lowest number of powers of momentum involved. It's a Taylor expansion of a sort. And then as you go to higher orders, you get more and more complex operators, but these higher order operators are suppressed if the typical momentum involved in the problem is small. So if you are at a specific density, you should be able to calculate the equation of state at any order. And as you go to higher order, the calculations are expected to improve. As long as these calculations improve, you know that you are within the validity of the effective theory, and you can calculate observables and estimate errors. So such calculations have led to very controlled error estimates for neutron-rich matter that exists inside neutron stars. And these calculations suggest that the effective field theory potentials and their predictions for dense matter converge up to about twice nuclear density. Now, there are still some issues that one has to deal with associated with how one regulates high momentum in these calculations, and these certainly need further study. But the calculations, very different approaches to the same problem, seem to give very consistent results, and these trends are very promising. I'd like to mention a very interesting recent study by Drischler and his collaborators, where they did for the first time a very systematic estimation of the truncation errors associated with this expansion. And the pressure energy density or the pressure density curves are shown in the plot here. And one can see that as you go to higher orders, for example, when you go from N2LO to N3LO, higher order in the expansion, you see that there is overlapping regions between the two calculations, which suggests that the convergence of the theory still is reasonable up to twice nuclear density. And one can now estimate the errors associated with the pressure at various densities. Now, for example, these neutron matter calculations can be extended to study matter encountered inside neutron stars that also contain a small admixture of protons. And our best estimate to date is that the pressure at about twice nuclear density in nuclear physics units is about 20 plus or minus 5 MeV per Fermi cube. Now, this is interesting because now we can start putting error bars on the equation of state, and hopefully this will help us constrain neutron star structure. The errors at low density, the density is much below 10 to the 14 grams per centimeter cube, are very small and have a negligible impact on neutron star structure. But the equation of state between about 10 to the 14 and a few times 10 to the 14, shown by the data point by the calculations in this figure, on the other hand, have a direct impact on neutron star radii. So what's shown here is the current estimate of the errors associated with the neutron matter calculations that I just discussed. Now, clearly, to construct neutron stars, we need a method to extrapolate to higher densities as well. And here one can utilize a very interesting feature of high-density matter, which indicates that the speed of sound in any phase of matter must be less than the speed of light. And that is because of a principle called causality. So the speed of sound is, the square of the speed of sound is related to the derivative of the pressure with respect to the energy density. And the largest it can be is 1. And so given that the derivative of the pressure with respect to energy density is bounded, you can easily use that to put an upper bound on the pressure allowed at any density larger than the density at which you can make useful calculations. So you have a natural, robust upper bound on the highest pressure achievable inside neutron stars, and that's shown by the dashed white line there. And the existence of two solar mass neutron stars also requires a certain minimum pressure for one to be able to support what we see. So together, these provide upper and lower boundaries to the equation of state that one can utilize to derive robust bounds on neutron star structure, despite lack of knowledge of the equation of state at these higher densities. So there are several authors that have studied how these bounds can be derived, and I'll just report on a recent study that used the most state-of-the-art effective field theory calculations and using the fact that you impose these extremal high-density equations of state to derive bounds on the neutron star radius of any mass. So what's shown in this figure here is the mass and radius of neutron stars using calculations that only go up to twice the saturation density. This is the density up to which we can currently do calculations. And what's shown here is the mass and radius relation for neutron stars constructed with that equation of state. Now, if we extrapolate to higher density using the speed of sound, by setting the speed of sound to the speed of light, then we produce the maximum radius neutron stars shown by the orange shaded region. So the central values are shown by the solid curve, and the other curves indicate the 1 sigma and the 2 sigma errors that are propagated through the high density equation state. So based on these calculations, the maximum neutron star radius has to be less than about 13 kilometers. Now, if we measure neutron star maximum masses, we already know that 2 solar mass neutron stars exist. Because 2 solar mass neutron stars exist, this implies that the minimum radius that a neutron star can have can also be calculated using the method I just described earlier, and you get a lower bound in the neutron star of about 9 kilometers. And if future observations, and if, for example, a recent observation of 2 binaries, perhaps a neutron star, one of the objects could either have been a neutron star or a black hole, has a maximum mass of about 2.6 solar masses, then you begin to find that the constraints on the upper and lower bounds in the radius improve dramatically. At the moment, we don't have evidence that this 2.6 solar mass object is a neutron star, but in the future, we may discover massive neutron stars with masses greater than 2 solar masses, and that would provide very strong constraints on the lower bound on these radii. Another important conclusion one can draw from these analyses is that if the radius of a typical neutron star is large, by large I mean greater than about 12.5 kilometers, or very small, in either case, it would imply that the speed of sound somewhere in the neutron star will have to change very rapidly. And that's interesting for several reasons. One can also use what we learned from nuclear physics and these upper and lower boundaries on neutron star mass radii to improve the data analysis that goes into extracting neutron star radii from tidal deformability measurements. And one such study by Capano et al. Found that when one includes nuclear physics, rather than just putting an upper bound on the radius of about 13 kilometers, we can now say that neutron star radii should lie between 11.2 and plus or minus about 1 kilometer. And so this is really a remarkable improvement in the accuracy with which one can deduce the neutron star radii. In the future, with more gravitational wave measurements, these measurements of individual radii for the neutron stars in the binary will improve, and one can hope for maybe an accuracy that is better than half a kilometer. And in that case, you may be able to find distinct regions of neutron stars with very similar masses. And if one finds such situations, then such constraints will likely help us discover very interesting phase transitions required to produce different radii for neutron stars that have very similar masses. A small neutron star radius has also important implications for astrophysics. It impacts our interpretation of surface X-ray emission. It has an impact on our understanding of how big the neutron star crust can be. It also has important implications for the outcomes of mergers involving neutron stars. If neutron stars are very small, then the collision between a neutron star and a black hole is unlikely to eject any material. And if such collisions do not eject any material, then there will be no electromagnetic signals associated with neutron star black hole mergers. And that has important implications for multi-messenger astronomy, where people, worldwide astronomy groups are trying to find counterparts to gravitational wave sources. Now, the other important implication of a small neutron star radius is that it implicates that the speed of sound somewhere in the neutron star has to be very large. And it suggests that the neutron star, the speed of sound at high density must be non-monotonic. While we can calculate the speed of sound at low density using nuclear physics methods, and at extremely high density using perturbative QCD, the speed of sound in the intermediate region is very hard to calculate, but we have neutron stars to help us out. And what we've learned recently from the small mass, from the small radius and the large maximum mass, is that the speed of sound is likely non-monotonic. So a simple extrapolation in which there is no maximum from low density to high density is very disfavored, as shown in this plot. And other curves in which the speed of sound has either a bump that exceeds this limit, which is 1/3, which is called the conformal limit, which is obeyed by many theories of dense matter, but not necessarily QCD, indicates that the neutron star interior certainly seem to violate this limit. And this suggests that some form of very strongly interacting relativistic matter is present in the high density cores. This form of matter could be achieved either through some smooth crossover or by an abrupt phase transition, as indicated by this black curve. Finally, in the last few minutes that I have, I want to mention that measurements of masses and radii are going to greatly improve, and they will inform us about interesting aspects of the equation of state. But measuring the quantum nature of the neutron star interior, especially quantum phases such as superfluid phases or related phases, which we expect to exist inside the neutron star based on theoretical calculations, are hard to detect by just making mass radius measurements. To understand whether such phases exist inside the neutron stars, we will need observations that can probe the thermal and transport properties of neutron stars. So that's because distinct phases at high density can have very similar equations of state, or the current uncertainty in the equation of state for two different phases may be so large that we will not be able to use mass and radius to distinguish between them. So in these cases, we have to look for thermal properties or spin evolution of neutron stars because they are much more sensitive to phase transitions and to the way in which matter behaves when it is heated to low temperatures or when it is spun up. So multi-messenger observations of dynamical phenomena in neutron star mergers and supernovae, which are likely in the coming decade, will provide valuable information in this context. So as I anticipated, I will not have time to mention other aspects of neutron star science where we use neutron stars as laboratories for dark matter. So I will just skip over these slides and conclude by noting that the future is actually very bright and loud for neutron stars. we've demonstrated that we can combine improved theoretical calculations of the outer regions of neutron stars with observations to infer specific aspects of matter at the highest densities encountered in the core. Current gravitational wave detectors at design sensitivity will see many events, expected to see in the tens of events a year, and some fraction of them will be close by so that we can extract useful information about neutron star radii. And the next generation gravitational wave detectors may be about 10 or 15 years away, but they would be revolutionary because they would have an event rate that is greater than 10,000 per year. And at that point, we would be routinely seeing neutron star mergers. As Anna will describe, the electromagnetic observations of neutron stars continue to provide extremely useful information. In particular, X-ray observations from rotating neutron stars may provide useful constraints on neutron star radii in the near term. We're also overdue for a galactic supernova. I haven't had time to discuss that, but the properties of neutrinos from a galactic supernova would also provide very valuable information about dense matter inside neutron stars and neutron star properties. So let me conclude by saying that there is tremendous potential for discovery, and it motivates advanced modeling and theoretical studies of dense matter to interpret these multi-messenger observations. Thank you.
So it is a pleasure to follow on from Sanjay. What I want to do is to introduce you to the Neutron Star Interior Composition Explorer, or NISER. NISER is an X-ray telescope that's installed on the International Space Station, and it's pioneering a new technique for measuring neutron star mass and radius, and hence telling us about the dense matter equation of state. Then I'm going to talk to you about what comes next. As Sanjay already promised, I'm going to talk a little bit about what the X-ray telescopes of the future are going to bring for us as well. What you can see here is the beautiful NISER mission badge showing a neutron star and the International Space Station and the NISER instrument itself. So let me start with just a quick recap. Essentially, what we want to do is to understand the neutron star interior. And as Sanjay's already mentioned, there's a lot of uncertainty about, first of all, what kind of particles essentially we're dealing with in the neutron star core. Is it primarily neutrons and protons? Do we have stable states, for example, of strange matter, either as deconfined quarks or in the form perhaps of hyperons? And then coupling that, of course, out towards crust models, where perhaps things are still a little less uncertain, but still somewhat uncertain in terms of composition as well. So we'd like to understand the possible states of matter, basically deep within the neutron star core, where the densities can get up to perhaps even as high as 10 times the normal nuclear density. Now, in trying to do that, what we do forms part of a spectrum of activity of trying to understand the behavior of matter across the whole range of temperature and chemical potential or density scales, from our kind of everyday world down in the bottom left-hand side, basically, of this diagram, across from the world of hadrons and nuclei up towards perhaps quark-gluon plasma or deconfined quark states. We have heavy ion collision experiments, basically dealing with exploring this parameter space at high temperatures and lower densities, edging up towards higher densities now. Neutron star mergers, basically sitting in this middle space, basically, and then old cold neutron stars, and that is what NISER is focusing on, basically up towards this low temperature, very, very high density regime, basically in the bottom right-hand corner of this plot. And as I said, this can take you up to 10 times normal nuclear density, potentially highly neutron-rich states of matter, and perhaps even stable states of strange matter, which cannot be formed in the laboratory. Okay, so how do we as astronomers go about doing this? Essentially, all of the techniques that we use follow this kind of loop that I'm illustrating on the slide here. In the bottom left, we have the uncertainties in the core composition. Are we dealing primarily with nucleonic matter, mostly neutrons with some protons, perhaps hyperonic matter in there as well, or perhaps some kind of quark matter state? Now, the uncertainty is basically in the forces between the particles and the types of particles that are present. We encode, Sanjay has said, in the equation of state. So this is the relationship between pressure and density. I won't talk about temperature too much in my talk because I'm talking about old cold neutron stars, and we tend to neglect temperature. If you're dealing with neutron star mergers and post-merger remnants, you need to worry about temperature in there as well. But what you're seeing here essentially are a range of different current equation of state models to give you some feel of the uncertainties in the current modeling status. We then need to translate that into something that we can measure. Unfortunately, we can do that using the stellar structure equations, and these are the relativistic equations of stellar structure to build neutron stars, taking into account also potential rapid rotation. And the equation of state is one ingredient that goes into the stellar structure equations to produce, for a given central density, a mass and a radius for that neutron star. If we perform those calculations for a range of essentially central densities, we end up for each model producing a mass and radius relationship. And again, here you can see the kind of range of current theoretical uncertainty that we're looking at, potentially radii from 9 kilometers up to perhaps about 15 kilometers. And ideally what we want to do then is kind of map this relationship out. So we still need to find something that we can actually measure, but the mass and the radius, together with the spin of the star, set its exterior spacetime. So the technique that I'm going to talk about essentially involves finding something such as X-ray emission from the surface that is affected by the exterior spacetime, in this case photons, for example, propagating away from the stellar surface towards a distant observer. Those photons and their behavior, their energies, for example, are affected by relativistic effects. And in principle, if we can measure that and model that, we can loop back to infer the mass and the radius. We can then go further back in the loop towards the equation of state. And ultimately, we hope back towards composition, basically on forces between particles. And that is the loop that we're trying to follow. So that is essentially what NICER is doing. So let me start by giving a little introduction to NICER itself. First of all, just to give you a general idea of the size of the instruments. Here you can see NICER before launch, basically in the clean room. Here it is shown here, slightly larger than a washing machine. And here you see the team of engineers, or ninjas, as my younger daughter called them, basically shown here. But this gives you a feel for how large it is. NICER was launched at the beginning of June 2017 on a Falcon 9, basically beautiful launch, and installed onto the International Space Station. And if you go along to the NICER website, you can find some beautiful videos of NICER being essentially unpacked and installed, greatly sped up, but it's a nice movie to watch, essentially along with your coffee break. The nice thing about having a telescope on the International Space Station is you can actually take movies on it. Many of our X-ray telescopes are free-flying, so once you've launched them, you never get a close-up of them again. For NICER, that's not the case. So I can actually also show you this beautiful movie, essentially taken of NICER in operation on the ISS. Again, greatly sped up. It doesn't actually move around that fast, but it gives you a feel for the kind of environment that we are working in. So here is NICER essentially moving around, and it was, okay, so here you see the detectors, basically around the front here. As you can see, we're tied to the space station's orbit and movements. We also have to contend with solar panels, essentially moving around in the background. Other instruments also in here as well. Sometimes there are astronauts outside doing operations around the space station. And one of the nice facts about NICER is it is built to withstand a kick from an astronaut, should that interaction happen when someone is outside, basically on a spacewalk, for example. So this gives you an idea of the environment that we're running within. So let me talk now a little bit about the technique that NICER is using. So it's to do with trying to tie in to a quantity that depends essentially on external space-time. So we're talking about essentially emission from the surface, where the photons have to propagate out through the potential well of a rapidly rotating relativistic object towards a different observer. And in NICER's case, we are using a technique called pulse profile modeling. And this depends on the existence of bright spots in the X-ray on the surface caused by very hot patches of emission. What you can see in this little movie is effectively the difference between having Newtonian gravity and starting to put in strong gravitational effects. And you can see some of the key physics basically illustrated here. For example, in the Newtonian gravity case, as the hot spot vanishes behind the star, you lose all emission completely. When you start to put essentially light bending in there, you can now essentially peer a little bit behind the star, and so the spot never completely vanishes. And then we add into that other relativistic effects, Doppler shifts, aberration, and so on, which also affect the emission in very predictable ways that we can calculate. So in principle, we know very well how for a neutron star of a given mass radius, what emission should look like to a distant observer if we put a hot spot on the surface. So how do we get the hot spots on the surface? The type of star that NICER is actually looking at are millisecond rotation pad X-ray pulsars. This is the simplest possible cartoon that I can show you of that system. These are non-accreting X-ray pulsars. Basically here, the X-ray hotspots arise due to particles being accelerated in the magnetosphere of the star, basically impacting the surface and causing the magnetic foot points or the polar caps to heat up to temperatures where they emit basically in the X-ray. We are going for millisecond X-ray pulsars because the rapid rotation essentially is the benefit. We then can use Doppler effects, essentially other relativistic effects, to disentangle the mass essentially from the radius. So let me now walk you through in a little bit more detail the pulse profile modeling process. So I've said we're using stars where the overall brightness is varying essentially as the star rotates, so that we can use these rotational movements and rapid velocities to disentangle information about radius. So what we do is we record as a photon arrives. This is a pulsar, so we know the spin of the star, and these are very, very stable rotators. So we can assign every photon that arrives a rotational phase, essentially, for that star. We also know the energy of the incoming photon. And here's the kind of simulated data set of what a pulse profile looks like. So every time a photon arrives, we pop it into a certain phase bin, and we pop it into an energy bin, and we build up counts. What you see here is an example with, these are two rotational cycles shown, one slightly kind of less bright pulse here, and one much brighter main pulse here, and spread out over different energies, and so a different spectrum that varies as the star rotates. So that is the high quality data that NICER is providing for us, and it's the soft X-ray telescope, so perfectly tailored for these rotation millisecond X-ray pulsars. We then need to find essentially a way of extracting mass and radius information. So first step is to build a physical model of what exactly is happening. So that physical model includes a number of ingredients. The first is relativistic ray tracing. And what I want to do is to say, okay, for a star with a given mass and radius, I want to be able to simulate what that data essentially should look like and then compare it to the observations. So in the relativistic ray tracing model, I have the mass and the radius and the spin. I put in other things that would affect what I see. The distance to the source, the angle of inclination I'm looking at it, how many hotspots do I have on the surface, what's their shape, what's their temperature, what's any beaming factor associated with the emission and the atmosphere, and I build up my model gradually that way. I also need to model the instrument that I'm detecting it with. If I'm producing simulated, essentially synthetic data, I have to follow it through an instrument response, and I have to model that. And then again, I want to compare that all to the real data. So having built my physics model, I then also need a way of statistically sampling across that parameter space. And we do this using Bayesian inference and large-scale statistical sampling, basically in order to extract essentially posterior probability distributions for all the parameters of the model. And that is not only the mass and the radius, but also the geometric parameters. Where are the hotspots, for example? What's the distance to the source? And for some of those things, we already have prior information from other means, basically that goes into the Bayesian inference as well. So for some sources, for example, we already have a good mass measurement from radio pulsar observations, or perhaps we have a good distance measurement as well, and we use that information as prior input. Okay, so let me walk through each step of this in a little more detail to give you a feel for how all these steps come together. Here is some real pulse profile data. This is the first source essentially that NICER examined in detail. Again, what you can see is the pulse phase here, 2 cycles shown, energy in kilo electron volts, and the number of photons going into each energy and phase bin. This particular source essentially is an isolated pulsar, 2 very, very clear pulses basically shown in the pulse profile, one slightly brighter, one slightly fainter. Just to give you a different example, this is one of the other sources we're currently analyzing. Here, the second pulse is much, much less distinct. Basically, then one bright main pulse and a slightly kind of hump-shaped shoulder here, which is essentially the second pulse. Okay, in terms of our simulation and inference codes, these are highly computationally intensive. Once you come, one individual simulation of a synthetic pulse profile takes about a second, but we have a huge parameter space to survey, and so we have to go to high-performance computing. So we're doing this on supercomputers. Our codes have been through a whole variety of tests. We cross-tested within the NICER collaboration a whole bunch of different ray tracing codes to make sure that our physics models were accurate. And then we've also run a series of tests on the inference that we're doing generating synthetic data, running it through the pipeline, and verifying that we can extract back essentially the parameters that we put in to some good degree of confidence. Okay. I already mentioned we have to model the instrument response as well. No X-ray telescope is ever perfectly understood. There's always calibration uncertainty. So the way that we chose to do that basically in the codes used in my group is that we chose to model the calibration uncertainty to include those parameters as an element of our model. So our Bayesian inference process also delivers us a posterior distribution on the effective area, essentially, of the instrument as a function of energy. And here you're seeing, for example, for the first source we analyzed, our prior on the instrument effective area model. And that is something we will also refine over time. Coming on to some of the other astrophysical aspects, this is where things get rather interesting. Because an ingredient in our model is the shapes and locations and sizes, for example, of the hotspots on the surface. And if you go and talk to a pulsar theorist and ask, well, what does a polar cap look like? This is a very, very complicated thing to simulate because you have to simulate return currents in the mesosphere and you have to simulate the heating pattern and energy deposition as well as then the atmospheric beaming. And there's quite a lot of uncertainty in that. Some simulations have kind of circular hotspots, some have arcs or crescents, basically, or rings even. So what we decided to do was to try and build parameterized models that could allow a wide range of surface patterns. And again, to search over that parameter space and to try as best we could to encompass the current range of theoretical uncertainty. So what we chose to do basically within the Amsterdam group results, we decided we would assume that we had two emitting regions because of the two clear pulse profile peaks in the first source that we were examining. And then we periodically essentially allowed the complexity of the hot emitting region to get more severe, if you like. So we started off with a very simple model, essentially of two circular hotspots. We could force them to be antipodal, or we could allow them to move around, so not to be antipodal, have different sizes and temperatures. And then we allowed them, for example, to have a different temperature ring around them, for that ring to move off center, and then to form structures by overlapping two circles, which allowed us to build essentially crescents. And the temperature of this one basically could be higher or lower. And then the other hot emitting region could be completely different in terms of its parameters. So that was the kind of model space that we were going to work through. So let me start by showing you our inference results, basically for the very, very simplest model that we started off by looking at. So this is assuming two single temperature circular hotspots, essentially, but allowing the temperatures of the two hotspots to differ. So what we end up with are posterior distributions for all the parameters. And what I'm showing here are posterior distributions, two-dimensional and one-dimensional, for mass, radius, and compactness. So we ended up finding, essentially, here you see radius, relatively low radius, uncertainties around about the 10% level, very, very well-defined compactness, mass to radius ratio, and the mass tending off towards quite a low value. The geometry had the Earth observer sitting down looking for one hemisphere, the two emitting regions in the other hemisphere, basically, but certainly not a nice antipodal hotspot, one opposite the other. And then we evaluate model quality. So we look at things like, what is the best scenario you can come up with for this particular model? How does it compare to the data? What are the residuals between the model and the data? What is the Bayesian evidence? What is the background emission that we predict as a result of this? That's also a parameter in our model because we have independent constraints on the background. And what is the maximum likelihood? So we had a whole sequence of model quality measures. And this model was certainly not the best one that we came up with. So we then worked through the sequence, increasing the complexity as it was needed, and evaluating model quality until we identified what we deemed to be the preferred model of the family that we looked at. So what I'm going to show you now is NICE's first mass radius result and the preferred configuration that we inferred. This particular configuration had ended up having one very small kind of circular hotspot, but in fact we're quite insensitive because it's so small to the detailed structure of this emitting region here. And one kind of very long crescent-shaped arc that spread around. Again, both emitting regions in one hemisphere and the Earth observer looking from the other hemisphere. Then we come on to the mass, the radius, and the compactness. The compactness remains extremely well constrained, basically a few percent level. The radius and the mass, we don't have any prior information on these at all. What you're seeing in the dashed line is the prior, and what you're seeing essentially in the solid line is the posterior distribution. We found a radius of about 12.7 kilometers with about a 10% uncertainty. And the mass, similarly, about 1.34 solar masses, but about a 10% uncertainty on the 68% confidence interval. So in terms of, as I said, we do various measures of model quality. So just to show you one of those, this is the original pulse profile data here. PI channel here being shown instead of energy, but this is a measure of energy against number of counts basically in phase bin cycles. This was the result of the kind of the best model basically that we found, and they look pretty good. And here are the residuals, and we were able to evaluate whether the residuals are at the level that we deemed appropriate. And this is just one of the quality measures that we looked at. In terms of how this gives rise to the observed emission, if you look at it from the Earth observer, that's what this diagram is showing here. Basically, as these bright emitting regions come into view, and both of them are really quite on the limb of the star, they give rise to the two different pulses, basically, that we see as the star rotates. So this was our first set of analysis. We had a lot of challenges to contend with as we went through this. The astrophysical challenges, the data challenges, how do we model the instruments, how do we work through the theoretical uncertainty in the hotspot pattern. We were not the only group to do this in Amsterdam. There was an independent group within the NICER collaboration led by Cole Miller, which also performed their own analysis. They made some different assumptions about priors on parameters. They modeled instrumental uncertainty in a different way by tying it into the distance. And they had a different parameterization of the shapes of the surface hotspots. Plus, they considered whether they might want a third emitting region in there as well. They came up with a fairly similar emission geometry, a small bright spot and a longer extended region, with the possibility of a third kind of less luminous region in there as well. And the masses and the radii that we got were comparable within the error bars. So different assumptions, different modeling procedures, but coming up with comparable answers. And all of these results were published together in an AppJ Letters Focus issue at the end of December 2019. So how does this compare with results from other mass and radius techniques? One of the techniques that's used often also with X-ray telescopes is not to look at the rotational phase-dependent emission, but to look at stars where there is essentially no rotational phase variation, just to look at the overall glow of an X-ray spectrum after, for example, a thermonuclear X-ray burst. So one of the state-of-the-art results is to do this kind of phase average burst spectroscopy using atmospheric models appropriate for bursting neutron stars. And I'm just going to quote one result, but there's a huge amount of them. And this is from a paper by Jonas Nattila in 2017. The results depend a little bit on atmospheric composition. Basically, there's also some uncertainty due to distance in there. But the radii that they are coming up with, 12 to 12.9 kilometers, are comparable to our results. So that's nice to see. And we can also think about comparing our results to the masses and radii inferred from gravitational waves as well. So let me mention just one of the many results that came out essentially after the binary neutron star merger that Sanjay also discussed. Basically, they measure some limits on tidal deformability and then fold those through equation of state models to determine essentially infer a mass and a radius. And what I'm showing here are two different possibilities, essentially for different equations of state, essentially distributions on the radii, essentially, of the stars and the masses as well. So what is clear is that the result that you get here depends on your equation of state model, although they are consistent, basically, with the results that we have. But it is worth thinking a little bit more about this dependence, essentially, on equation of state model, because this is a really important aspect of how we use the masses and the radii that we infer from NICER and how we compare and combine them with gravitational wave results. As Sanjay mentioned, an equation of state model is pressure expressed as a function of density. So basically, there are lots of different parameterized equation of state models that people are considering, motivated by first principles physics, but perhaps simplified into a parameterized function. One example is a piecewise polytropic equation of state, perhaps with some kind of chiral effective field theory motivated low density extension. That's a very common one. There have also been speed of sound-based models, tying into what Sanjay said as well, where you parameterize your equation of state in terms of speed of sound parameters and look to infer those parameters back. So one thing, you can pick a physically motivated set of priors on those equation of state models, but you have to be a little bit careful. Let's say that you pick your parameter ranges in order to span a range of equation of state space. And you say, okay, I'm going to pick uniform prior distributions on each of those individual parameters. That doesn't give you uniform coverage of an equation of state or an associated mass radius band. And what you're seeing here is effectively the prior on your equation of state space that results from choosing uniform priors on the equation of state model parameters. But when you combine it into a function, it gives you a peak essentially towards that central pressure density space. And that is the prior distribution on your equation of state model. And it also translates into a prior distribution basically on a mass radius band. And this is not coming particularly from physics, it's just coming from parameter choices and prior choices. So by choosing uniform priors on individual parameters, you are starting with a prior that is strongly biased in this particular model, for example, towards about 12.5 kilometers. And similarly for speed of sound, we call this the heron. Basically, your prior is trying to push you in this way. So when you try and infer equations of state, you need to look carefully at what the priors are on your equation of state model, and you need to make sure that your data is sufficiently good to actually push you away from that and start determining what you're actually seeing, because this is not physically motivated prior, it's an accident of the way that you parameterize things. So let me come on to cover what we've learned about the dense matter equation of state so far. So what you have to be careful is choose, if you're going to combine with gravitational wave data and other data, pick one equation of state consistently for combining everything and understand the priors on that model. So for example, for the piecewise polytropic model that I showed you, here again is the prior, and this is just starting with the full region allowed by the whole model. We then start by putting in the high mass radio pulsar data, because that cuts out a lot of parameter space, and it moves your prior basically to the dotted and dashed lines, 68% and 90% prior distributions over here. But again, you can still see, you're kind of tying in towards this 12.5 kilometer region. Let's say we then add in the gravitational wave data. This moves you to the green regions here. It pulls you down in radius a little bit, basically in terms of your distribution. So you're updating information with gravitational waves, and it's pushing you down a little bit. Let's add the nicer data now back in, and at the moment it pushes you back up a little bit again in terms of the radius and the mass radius relation. But again, a lot of that is still determined, if you look at information gained, by the prior on your equation of state, not the results coming from gravitational waves or from NICER so far, because those measurements are not yet good enough to give us really, really tight constraints. But that will improve over time. So where do we go from here? Well, we also need to start thinking about the implications for the astrophysics. I said the hotspot models and geometries that we use are an essential part of the model, and they are tied, we think, to the magnetic geometry of the star. So the structure that we inferred for the NICER pulsar implies that we have a very complicated magnetic field that is not a simple dipole. And this then has consequences for the multi-wavelength emission for this particular pulsar. And so we now need the pulsar theorists to go back and try and figure out if this makes sense, and also those working on magnetic field evolution for neutron stars. They may come back and tell us, we just can't make those shapes that you have. The models that you assume for the hotspot geometry need to be revised. You need different models and perhaps different priors on the configurations that you allow. So that part of things is now going on. In terms of next steps for NICER, NICER is extended until at least the end of 2022. What you're seeing here are, again, mass and radius and several different models shown as colored lines. This light green ellipse shown here are the 68% and 90% confidence intervals, or credible regions rather, for the pulsar that we've already analyzed, J0030. So this is a fairly uncertain measurement at the moment. We have two sources we're currently analyzing for which we have a good prior on the mass, basically by independent means from radio timing. One is this pulsar that's around about 1.4 solar mass, very, very tight constraints. We're currently doing the pulse profile modeling for this one. We have about 1 megasecond or so of data basically together on this, and we would expect the credible region to be smaller, correspondingly smaller. So it'll be interesting to see if that one agrees. And we're also studying this very high mass pulsar that's recently been reported by Cromarty et al. And so we should have a region up here at the top range of the diagram as well. And as I said, we need to think more carefully about the implications for neutron star evolution, a magnetic field, and that may lead us to revise some of our analysis as well. And then there are a couple more sources in the pipeline too. So I will quickly say a couple of words about beyond NICER. The NICER sources, rotate up to 200 times a second. Okay, so they are fast, but they're not the fastest neutron stars that we know of. Nor are they the fastest rotating neutron stars with bright spots of some kind to which we can apply pulse profile modeling. We have stars that can rotate, up to 600, 700 times a second, essentially with bright X-ray emitting hotspots where the relativistic effects are stronger, and hence we can hope to get, in principle, stronger constraints on the radius as a result. And these are the accreting neutron stars. So in order to get those, we have to collect an awful lot of photons. And we also need a hard X-ray telescope because the emission is a little bit higher photon energy than for the NICER sources. So this means we're looking at the next generation of free-flying large area X-ray space telescopes, following on from the Rossi X-ray Timing Explorer. Some of those telescope concepts, this one in particular, the Enhanced X-ray Timing and Polarimetry mission, which will be a joint Chinese-European mission, basically currently in early phases of study, but looking very, very promising. This would have a large area, several square meters, but also an X-ray polarimeter, and that's something that can potentially constrain the geometric parameters. So that is something we need to look at doing. An alternative is StrobeX, and that's a NASA probe study concept where the study is now completed, being considered by the Decadal survey at the moment. So this would again be several square meters, soft and hard energy detectors, but not with the polarimeter. But we could also use this as well. We do, however, then need to think carefully about the astrophysics. Again, these parameterized models of what is allowed in terms of the number and properties of the emitting regions. We need them to be physics-driven, ideally, and we also need to be able to handle the fact that they are not as stable as for the NICER sources. For example, for accreting millisecond pulsars, basically where you have emission coming from hotspots where matter is accreting on, we know that those change on timescales of weeks. So we have to have the telescope large enough to deal with that variability. And we also have stars where the surface is exploding. These are thermonuclear burst oscillation sources. Bright spots develop in many thermonuclear. We don't understand why at the moment, but they can be highly mobile. And so we need to figure out if our analysis protocol essentially can handle that variability as well. So let me wrap up with where we are. NICER has shown that pulse profile modeling is a viable technique. And we have our first result after a lot of work on the details of the pipeline at the 10% level for mass and radius, but we are certainly expecting tighter constraints with the next source that we're analyzing. The analysis has thrown up a lot of challenges on the data, the instrument, and the modeling. It's clear that the astrophysics matters, but the bonus is that in addition to getting mass and radius, which is our kind of core science goal, we also infer interesting astrophysical properties as well. NICER will give us maybe 5, maybe 6 results along these lines, but with the next generation of X-ray telescopes, we're looking at upping that to much tighter measurements, and in principle getting about 20 measurements spanning a wider range of mass and radius. So I'll stop there.